My old colleague Henry Bain called me last Sunday, and he asked me if we could do a meetup in Rotterdam, if we could host it with us, and that would come to Amsterdam or to the Netherlands, and he would love to do more sessions. And I thought, wow, cool, let's do that. When? Yeah, next week. Oh, wow, that's on short notice. No, I mean this week. Wow, what the fuck? I thought, but okay. Maybe it's good to tell. I am here at IBIS for 2 weeks now, so it's really on short notice. But we did it, and I'm glad to see you all here. Welcome at the Grote Handelsgebouw. Grote Handelsgebouw is the symbol of reconstruction of Rotterdam and the Netherlands after World War II. And construction is all about what we do here at IBIS. We develop software for construction, civil engineering, and asset management. And companies like Heijmans, BAM, Ballas Nedam use our software to calculate great projects in the Netherlands. Construction is also a very, how do you say that? Conservative market, traditional markets. Thank you. So we want to innovate the market, and to innovate it, you have to have technology. And we talk about technology. Then you think about Seth, and we think about Gerald. Thanks for being here. And yeah, I don't want to make it a big talk, so let's get started.
All right, thank you.
Yours,
How is everybody today? Good. So today I'm going to talk about machine learning. It's so when people like sell this stuff, they call it AI, right? When you actually do this stuff, it's called machine learning. And so that's how you know if someone's selling you something versus somebody is like trying to tell you how to do it. And so today what I'm going to do is I'm going to talk about machine learning. How many of you have done machine learning already? Okay, so some of you have done some already. I'm actually going to start from the beginning, and I'm going to show you how to think about machine learning. And then once we start thinking about machine learning, I'm going to show you how to start understanding neural networks. And then neural networks is just is the old way of saying deep learning, except that the layers in the middle, it's deep. We don't know how many constitutes deep learning, but however many layers, and you'll see what I'm talking about. And so what I'm going to do is I'm going to go through the whole thing, and because there's not very many of us, like just stop me if something doesn't make sense, and I'll explain it in a different way, right? Because my job is to tell you how this stuff works, and if you don't understand, that's really my fault. It's not yours. And so I take that kind of seriously. And so let me know if you saw my session yesterday at Tech Summit. I went really fast, and I showed just a little bit of the stuff that I'm going to show. But you're going to see a little bit of that repeated here. But again, it's going to be much slower, and hopefully it makes sense because there is some maths involved. And but it's not hard math. It's just once you wrap your head around it, it makes sense. But again, it can be hard if we don't think about it the right way. And so my job is to help you think about it the right way. Does it make sense? Okay. Well, yes. Yeah, if you want them, sure, I'll send them to you. Yeah, absolutely. Don't if you want these slides, just tell me and I'll send them. I'll put them wherever you tell me to. Yeah. The reason why I have this slide is because now everybody's like AI, and their manager will come down to you and say, "Hey, can we add some AI to our software? You know, so we can tell everybody like we're like using AI." We're doing AI, right? What does it even mean to do AI? I mean, you see what I'm saying? And so that's why AI is kind of a marketing term, but machine learning is the actual engineering. And you're going to see once we get done that, like, this is just another way of doing code, but different. And once you know what the difference is, then all of a sudden everything makes sense. And then the stuff that Microsoft actually offers in AI isn't as exciting as some name of a robot or some speaker that talks to you, right? It's actually, when you get down to it, it's the actual stuff you need to make AI. And so that's why Maybe we should talk about it with robot names or speaker things, but we don't. So let me tell you about machine learning through a story. How many of you work for a bank? Okay. So bankers. So imagine you work for a bank, and your boss, Sally, she comes down and says, "Hey, we want to do something new, and what we want you to do is we want you to write an algorithm that detects when someone like gets their check scanned. You know, like they sign. Do you guys use checks here still? Not, but you know what they are, right? Your mom still uses them, or your dad, right? They still use checks. So imagine like they put their checks in, but they never follow instructions, and you need to write an algorithm to turn the check upside down, right? If it's upside down, it flips it. It says flip it, otherwise it doesn't. But your bank is real cheap, and the only checks that you have a black stripe at the top. Could you solve that as a programmer? Yeah. You look at the picture. It always comes in the same size. You start scanning the pixels at the top, and if most of them are black, good. If they're not, flip. Right? Easy. You got this. And so you write that in 20 minutes because he's a good bank dev, this guy right here, right? And after that, the marketing guy comes down again and says, okay, so your boss really loves his cat. And just this one time, what I want you to do is I want you to write an algorithm because he wants now to put a picture of his cat on his check, just his. And so now you have to fix the algorithm. So what do you ask the manager for? Do you have a picture of a check with the cat on it, right? And then you're clever because you did the black pixel thing. And so you look on the picture, and since you have it, there's some tricks you can do, right? You can be like, okay, so looks like the cat's like smiling, and at the bottom, you know, it has his paw in this area. So I'll just check for that, right? We're programmers. We will come up with a way to solve it. And so 20 minutes later, he's like, I'm done. It works. And then the manager comes down and says, this was such a good thing that we want you to be able to do this for any picture, for any customer, for any check. Because you already did this, and you're such a good dev that you should be able to do it. It's super easy, right? It's just this one thing. They always tell you that. He's laughing because anytime someone comes to a programmer and says, it's just this one thing, you're getting hosed, right? So do you see there was like this weird something that happened between the picture of the cat and any picture, any check? What was the weirdness that happened? It feels like one is squishier than the other, right? Like it's like, oh, well, how do you could be clever and be like, hey, can we put like a black box at the bottom right-hand corner, right? You try to figure stuff out like that. No, we want any picture, any check. And there's a lot of problems that we work on as computer people or as programmers where it gets into that squishy area, right? Where we're changing a 0.5 to a 0.7, or we have to add another if-else statement. Right? We've all written code like this where we feel like we have to take a shower afterwards. Right? We've all done this. It enters this squishy area of like, what do I do now? And in that squishy area, that's where machine learning fits in. Okay? The thing about machine learning is instead of us coming up with a series of steps to solve a problem, we instead give the computer examples of the right thing, and it will figure it out. That's the difference. So coding now for AI, instead of writing some steps, you're collecting data with examples of things. So here's a check, it's upside down. Here's a check, it's not. Here's a check, it's upside down. And you got to give the computer all these things, and then you train it, and then it either works or it doesn't, or you train it and it works, and then out pops this model, and that's the thing that you're executing now. Model. Make sense? So the purpose, and you probably read this already, but my story was to help like clear this up. The system figures out what the person wants based on examples, and what we're doing is we're giving it data so that it figures the thing out. Right? And that sounds a little mysterious, but you're going to see that it's not so mysterious once we get going. Does that story make sense? Because I feel like I feel like we talk about AI a lot, but we don't talk about like what is it trying to solve. And it's that squishy area where we're starting to get into this search space that's way too big. Right? With the black stripe, it was easy. With a single cat, it was easy. If you would have added like 10 different pictures only, it's easy, right? But once you get into the any picture, any check, any customer, that's a problem. And so that's where AI fits in that weird squishy algorithm area. And you all have problems. You all have challenges or problems you need to solve that are in that squishy area. And so hopefully you'll see how to solve that. And like I love explaining it this way because as programmers, we're like, oh, okay, I know where this goes. Whereas before, people are like, hey, can I put AI in there? And you're like, what are you talking about? Right? We're building a point of sale system. We just need to put numbers in and put a record in the database. Where's the AI, right? There's no squishiness, okay? But the thing about machine learning is it always has to start with a sharp question. And there's really only 5 questions that machine learning can answer. But if you think about it, like if you combine these 5 questions together, then you can like feign intelligence. Like for example, driving a car around, you can reduce to a set of yes, no questions. Should I turn left? Should I turn right? Should I not hit this woman in the middle of the street, right? In America, we had a problem with that. It didn't answer that properly. Yeah, right? So these are the 5 things that questions that machine learning can answer, right? So how much or how many? Which class does this belong to? And if you remember, the check problem is this second question. Does it belong to the right side up or upside down class? The third is, are there different groups? Does it belong to a different group? Is this weird? Which option should I choose? Those are the only 5, but they have fancy names, right? This is what you probably heard them called if you do machine learning. The first one is regression. The second one is classification, clustering, anomaly detection, and recommendation. We're going to focus on classification today only, okay? But the other ones, you'll see that there's similar ways of doing it, right? Yes? It could be. You could say, is it weird or not? But the algorithms for this are different than these ones. Like you can use algorithms like these ones for this one, but you look at them differently. And so that's why we separate it out, because mathematically it's a different problem. Good question. Yeah, absolutely. By the way, if you have any questions, just stop me, right? And if something's wrong, just tell me. And I'll fix the slides before I put them up so it looks like I was saying the right thing. Even though he is recording this. We'll just have him like right over it, right? It'd be cool. All right. You probably heard these things also called by either supervised learning or unsupervised learning, right? Supervised learning is where you actually give it like examples with the right answer, like the check and upside down, the check not upside down. Unsupervised learning is you just give it examples of things and it figures it out. And so that's another difference, right? There is really no right answer here. You're just looking for weirdness. Good question. Any other questions? So far, it's pretty simple, right? Okay. Okay. So let's talk about the process of doing this. The first step is you have to have a question, and then this kicks off this process. Once you have the right question, remember, machine learning is all about the data. So if you don't have any data to answer the question, you have a problem, right? And so the first thing is you have to identify what data you have. Do you have examples of checks that are upside down and not? If you don't, you need to start getting some. So for example, a lot of people ask me, well, I want to do AI. I'm like, okay, what data do you have? Or no, sorry, what question do you have? Well, we don't know. Well, what data do you have? Well, we're not storing it. We'll save all your data because you don't know what question you're going to have. And so now there comes this problem of, because these things get smarter the more data you give it, right? And so now there's this question of, well, how much should we save? Because, for example, you might have IoT devices giving you sub-second records. Do you store all of them in perpetuity forever? Well, there's not enough space. But you might want to save as much as you can because you might have a question about that later on. And so you always have to start with a question and then look at the data. Once you do get the data, though, it's always almost ugly. Right? And I'm going to do this. I'm going to go through this one more time with a concrete example. So you have to actually look at the data, explore it, analyze it, change it over to something that the machine learning algorithm is going to understand. And this is probably where you're going to spend the majority of your time, is in this like garbage.
And that's probably what you see now in OneDrive with photo recognition.
What's that?
The photo recognition
Mhm.
is right. Say landscape.
Mm-hmm.
You hope it gives you landscape.
Yes, yes. And by the way, you train it with as much data as you can. And if it hasn't seen something, it's going to be terrible at it, right? And when I say it hasn't seen something, you're going to, like, I am not an AI mystic, you know, that people say this is magical and blah, and like this will change everything. It is going to change everything, but there's no magic about it. If it hasn't seen an example of what you want it to learn, it won't do it, right? I'll give you an example. Cognitive services, I just learned today, a good one of these great people took a picture, and cognitive services said, hey, it's a man with a hat, but he was wearing a turban. It's not the same thing. But it's like a 3-year-old. I'm sorry, you've never seen a turban. Let me explain what it is, right? And so you have to give it pictures of it to understand it. And so once you do that, then you build the model. This is the exciting part that I'm going to focus on, right? Because we're going to pretend that all our data is clean, and then you use the model to predict. Let me summarize this with an example. So the first thing is you have some data. And let me tell you what the question is. You work at a tennis shop, and you want to know if you should hire, when you should have Billy come in to staff the courts, because that's people play only when certain things happen, right? And so the things that you're keeping track of is the outlook, what the temperature is, and if it's windy or not, and then whether people play or not. And so now you want to come up with something that will tell you, yeah, these are the 3 things. We call them the features. And once you have the features, you know what the answer is, but you're going to build an algorithm such that when you give it a new X, which is whether it's sunny, whether it's outlook, temperature, windy, it will tell you, yes, they will play or no, they won't. And maybe even with a confidence score, right? That's what you want. But in reality, the data always almost looks like this. You're like, Bill always puts stupid things into the database, right? Or you have data that's not missing, right? What does it mean that it's kind of windy, right? And if you work at a bank, this is probably even worse than this, right? Like bank DBAs should be on the dirty job shows because this is horrible data. But you have to go and fix this. Often this is called yak shaving in programming terms, which is any apparently useless activity which by allowing you to overcome intermediate difficulties allows you to solve. This is yak shaving. This is the worst part of data science. It's the part no one talks about, but you have to do this. Like if you have a data scientist, they're doing this all day, right? This is what you're doing all day, right? It's terrible. We want to do the model stuff, right? Because, I mean, that's the exciting part. It's the algorithm part, but that's what we're doing. Once you do that, you have to convert it again to something numerical too, because algorithms really only understand numbers. There's some exceptions, but not many. It's almost all numbers. And then you build a model. So for example, how would you decide this one? Like, let's just say you had this example down here. What would you decide to do? Play or not play? Well, what we do in our brains is we look at the first column, we're like, okay, it's sunny. Where are all the sunnies? Okay. This isn't telling me something, but it's telling me I should maybe not play, right? We look at low, and anytime the temperature is low, well, crud. Looks like this one's telling me we should play. And the last one is no on the windiness. And the windiness looks like, okay. The windiness is telling me something, but we can't, how can we be sure? But that's what we do because as programmers, we try to come up with something. But the best thing to do is let the computer come up with this. This is a decision tree that the computer made up. Once you have this, you use this to predict, right? Play. The outlook is sunny. Okay. The temperature is low, then yes. And this is a decision tree algorithm that it will, if you give it the data, it will figure this out, right? But again, we're not going to focus on decision trees. We're going to focus on deep learning in this case. So far, so good. There's a four-step process. So the question that I often get is, how do you know if it's working? Yeah, but how do you, like, for example, let's just say you're building a machine learning algorithm to detect cancer. Do you just like train it and say, okay, here you go, good luck? Yeah, so what you do is you separate your data out. So let's just say you have a million records. You take 80% of your data, you build a model on that, and you test it on the balance. Nowadays, because models are starting to become more complicated, you also can separate it into something even more succinct. Like, for example, you train your model on this, and then you test it on your dev set. And you're like, oh man, this didn't do very well. Let's change some hyperparameters and then go again. And you just go here. And once you're confident it really works, then you can move it over to the test set. Right? And the thing about it is, like, if you do really good on this and you do really bad on that, something's wrong. Right? Generally, that's a problem called overfitting. It means that you train, you're like, it knows really well what you gave it. And then it goes out in the world and is stupid as heck because all it does is remember what you used to train it. And so that's how you know how well it's doing. But then there's also this other nuance of when you say how well it's doing, you usually are thinking how accurate is it? But there's even more than that. Right? And this is an interesting table. You can actually look this up because there's a name for this, there's a name for this, there's a name for this side, and there's a name for this side. But I don't know what they are because we don't care. Right? We generally, we're only focusing on accuracy, precision, or recall. Recall is how good are you at guessing the truth. Precision is when we guess the truth, how good are we? A very subtle difference, but the difference is important, right? Because, for example, if you're not sure about a cancer diagnosis, what do you say? Go get it checked, right? So do you want better precision or better recall? Well, when it comes to truth, we want to be very accurate, right? So I would think maybe recall. And that's important too. It turns out that you can actually get a measure, because it's hard to like optimize a model. And sometimes when there's a slider like in Studio, Azure ML Studio, there's a slider that will let you like fix precision versus recall, but the other one will suffer if you make the other one better, right? Then there's another one. If say you just want to have one metric you optimize, you can actually come up with a score between these two called the F1 score. That's the harmonic mean between them. It just tells you how well are they together. And so it's funny that it's called a confusion matrix, right? Because this seems a little confusing, but accuracy is even more subtle than just how many did I get right, right? And so those are the two other things. Is this good so far? Okay. So we're going to now move into the problem of, like, now that you figured out this check thing, because figuring out if a check is upside down or not is actually not too hard for the computer. Neither is this. Now they want you to figure out like the numbers that they hand wrote. And they already have an algorithm that pulls out like each square of the number. So how do we solve this one? Right? Well, we need to come up with something that looks like this. This is what we understand as programmers. We were going to get it. Once the picture comes in, then we want to get a number out. And it's either 0 through 9. Super easy. That's what we want to write. In general, machine learning is about making functions that look like that, but we call them h of x. And the question is, well, what is the h, the function, and what does the input look like? And once we start getting into this, now we're going to start getting into like machine learning. Okay? So let me show you this example. Instead of pictures, we're going to come up with a machine learning algorithm to solve whether the pixels are mostly horizontal or mostly vertical. Right? So this one right here is horizontal, or sorry, vertical. Sorry, I'm upside down time-wise. This one is horizontal. What about this one? Horizontal. And this one? Vertical, right? And so as a programmer right now, you're literally thinking, this is easy. There's 9 pixels. I can figure it out with an algorithm with a bunch of if statements, right? Right. Yes.
Maybe also check the intensity.
Yeah. The intensity is different. Like I automatically generated these. This is synthetic data. You can see all of these ones have like solid colors. And then once you get into like we were starting to repeat, you can see that they start to change, right? I uniformly at random slows down the intensity. But yeah, but it's still mostly horizontal, right? It's still mostly vertical. No, no. But you're still, as a programmer, you know, okay, there's a number there, right? But what if there's a little noise, like somebody spilled their wine on 1 pixel? Trying to think how that happened. It's very precise. It's still mostly horizontal, right? But if there's a little dot here, sorry, vertical. What's wrong with me? I don't know what's happening. So the question is, what does the input of the machine learning algorithm look like? Right? Remember, for supervised learning, what we're doing is we're classifying this. We need to have the right answer and the data. This is what it looks like. Now, you're probably thinking, well, Seth, this color is white. I just reversed the image, right? That's all I did, so that you can see it better. Otherwise, you get like these weird other things, and our eyeballs would be like thinking of the opposite thing. So here is the right answer. This is mostly horizontal, 0. This is mostly vertical, 1. You see it now? You can see that like this is how it's, and I made this because again, we're trying to solve the digit problem, but I want you to see like this in smaller form so that, because people were complaining like when I did this talk in January, they're like, I can't see the numbers, Seth, there's too many. So this you can see, there's 9 things going on, right? That's the X that goes in. From here over, this is the X, right? And we want the machine learning algorithm to spit out yes or no. That's the X. We good so far? So the question is, well, we need to find an H. We need to find a way to separate the yeses and the nos. So let me show you. What I'm going to do is, let me go over here. Oh, my mouse. Let me close this here. I have too many things open. I am going to open up this Excel sheet, and we're going to figure out a way to separate this data right here. So this is a classification problem. How many features do we have? This one, I'll give you a hint. Feature is singular. And then we have 1 label. What would you do to solve this machine learning problem? You want, because now the new X is coming in, which is a number, and you got to spit out true or false. Look at the optimization boundary. Okay, what did someone else say? Greater than 5. How do you know that? Okay. What if you have a billion numbers going all the way down? Well, it turns out like I think you're mostly right. So I'm going to go like this, and I'm going to sort this data by feature, and you're going to start to see a little pattern here. Do you see it? So for this stupid problem, the result is return X less than 6. Right? So if you're looking at this problem, because we only have a string of numbers, and we want to learn how to separate the two, we want to come up with a function that will separate the two. If it's a special kind of data, you can find a spot to like cut that string of numbers at a single point, right? What does that look like in 2 dimensions, though? So let me Control Z this and close it. What about this one? What's the best way to separate this data? You make a line, right? You make a diagonal line. So right now it's learning this diagonal line itself, right? It's just going through every point and finding the best line it can. So what if you're in like 3 dimensions? Find a plane. What about in 4 dimensions? A cube, right? What about in 5 dimensions? Hypercube. What about 6 dimensions? We ran out. It's hypercube all the way till infinity dimensions. right? So we found a way to separate data, right? We figure out a line. Well, the cool thing about a line is that there is a really interesting property about lines. We all know how to make lines, right? Y equals mx plus b. Remember the m for our first example, right? Y equals mx plus b is just moving it over 6. So the b becomes 6, right? And m becomes 0. Right? In 2 dimensions, now we start to get into slope. So how do we mathematically represent this, right? That's the question. Let's see. Oh, I wrote that. Yeah, that was mine. We all write our own stuff sometimes. Yeah, it's my machine learning sample thing, right? Because then like you can see stuff, and I'm not going to talk about kernels, but this is not separated by a line. So that's a problem, right? So let me tell you about this special algorithm that we've just invented to form a line, right? What we're going to do is we're going to take all the x's that come in, all 9 of them, multiply them by some number, we'll call it w in this little node. So x1 times w1, x2 times w2, x3 times w3, all the way to x9 times w9. Then it's going to come up with the multiplication, and then we're going to add them all together. You're probably thinking, what is that? That doesn't make any sense. Well, we wanted to make a line. And there is this really interesting relationship. This thing, like this is another way to look at it, right? All the x1s are coming together and multiplying, and then they're all getting married. Right? It's like a huge marriage. All the family members, like when you get married, you know, when you have more family members, it only multiplies the problem. And now you have all these problems added together. I thought that would be funnier than it was. But everyone's like, oh, yeah, that's what happened to me. Everyone's feeling all down. I'm sorry, I'll use a different example. But there's an actual name for this thing. Do you know what it's called? When you take 2 strings of numbers, multiply them and then add them, it's called a dot product. You remember this from your math class? Vectors, like all vectors are just a bunch of numbers that you store in an array. That's how I think of vectors, arrays. And how do you get 2 arrays and put them together into one value? Well, you multiply each of their constituent parts and then you add them all together. Called a dot product. And there's a really fun relationship between these things that maybe you haven't heard of. That's another way of writing these, right? This is a W that represents that array. This is the X. And when you write it like this, it means the dot product. You're transposing X and then doing like a matrix multiply that makes a single number. Remember, don't make it harder than we're taking some X's, we're multiplying them by some W's, and then we're smushing them together by adding. But this thing has a really fun relationship because let's just say W is only 2, then this represents a point in space. Right? And this symbol says how long is it? From 0 to that thing, how long is it? From 0 to x, how long is it? So that's what this says. The length of these multiplied by the angle between them is the same. This will give you exactly the same answer. Did you know that? And this always equals 0 at a very specific angle. Always. And it's when they're perpendicular to one another. Yeah? Does that make sense? So when you take 2 vectors, let's just say this vector stays the same and this one always changes, right? For all of the vectors where this dot product equals 0, all these vectors form a line. Yeah? And what's even better is that if this vector is not equal to 0, this multiplication or this dot product, then it's either negative or positive. If it's positive, it's on one side of the line. If it's negative, it's on the other side of the line. If it's 0, it's on the line. So now we've figured out a function h that when given a new x, we can predict negative or positive, which is true or false. So now what we need to do is we just need to find the magic w that does that, yeah? We good so far? And this is what this looks like, right? You have all these, all the horizontal ones are over here, all the vertical ones are over here, but we're only looking at 2 pixels. there's actually 9 pixels, and we have to find some hypercube in 9 dimensions to separate the two. And there may not exist a W that does that, but we got to find the best one. So now the machine learning problem for us is we found an H that we can use. We find this W, and then I'm going to add something called the bias, right? Because if there's no bias, that means the W is always centered around 0, and the bias just moves the line over a little bit. You might remember this as the y-intercept. Yeah, and so now we have to learn a W and a B that will get us the best answers for all of these things. Yeah? Are we okay so far? Okay, so far we've only talked about this thing called the dot product. We figured out that the dot product of 2 vectors is 0 along the plane, along the line that's perpendicular to that W vector. And if everything's positive, it's on one side, everything's negative, it's on the other side. Okay, so in reality though, our data looks like this. Because now we're trying to figure out numbers, right? That was the real thing. If you squint, what number is that? 0. These pictures that are coming in are 28 pixels by 28 long, which is 784, which actually looks like this. Remember how we had our vectors with like a 1 or a 0? There was just one column here, and then we had the 9 over here. This is a lot bigger. And now our answer is different, because each one of these spots represents the number that it is. So 0, 1, 2, 3, 4, 5, 6. This is the number 7. This is the number 2. What number is this one? 1. This is 0, 1, 2, 3. This is 4. This is 1. You see that? But that's a problem. Remember, the thing we made up only gives us a 0 or a 1. How do we fix that? Well, let's just add more. Right? So now we're going to have 784 X's multiplied by 784 W's for each one of these. Remember? And so there's got to be a fun way, there's got to be a really nice way to stack all the W. Because remember, each one of these has a W vector. There's got to be a really nice way to take all of these and stack them up together. And you do. You stack them up in this thing called a matrix. I mean, it's pretty stupid, right? So then this thing, just like we did before, dot product, we take this, like imagine taking it, switching it over, right? And then boom, dot product. You just take it for each one of them. You do the dot product, right? Then you add this bias term, and then you get all the Y's out. Do you see that? I mean, this is not mystical. And if it's hard, it's okay. Like, I've spent 10 years looking at this stuff, right? It's okay if it's hard. If I'm saying it's easy, I'm saying it's easy because I've looked at it for 10 years. Right? But remember, the problem we had before is we had a little W that gave us one answer. Now we have a big W that gives us all these answers, right? And then we have all the B's that like offset, right? And create this really interesting hypercube. Are we okay with this still? Okay. Stop me if this doesn't make sense. There's no shame. I'm just barely understanding this. Okay? So now the question is, how do we find this magic W? Right? This magic W in such a way that, like, you could go for that 9 by 9 one, you could probably go and systematically figure it out yourself, right? If I put a 0 on the first call and a 1, right? But you're going to find that there's not a really good answer for that particular problem, and that's on purpose, right? Because this is actually, that data set is part of a lab that I do to teach Tensor Flow. And if it was linearly solvable, then it would be super easy, right? So how do we get W? Well, we want to find a W, and I'm going to rephrase this. We want to find a W that minimizes the mistakes that we make. So that anytime a new X comes in and we multiply it by W and add B, it gets the right answer as much as possible. So how do we do that? Well, whenever you see the word minimize, you should automatically think calculus. If you don't, from now on, whenever you see minimize or maximize, because maximize is the same as minimize, you just multiply by a -1. Minimize, so whenever you want to minimize something, think calculus. And let me explain why that is. Here is this function now. Remember, this is our magic function h. and this is the right answer. What do you want this value to be for every x? 0, right? Because let's just say you guess horizontal, which is a 0, and the right answer is horizontal, which is a 0, you get 0. If you guess 1, and the right answer is 1, which means it's vertical, you get 0. If you guess 0, but the answer is 1, you get a -1. And then you add these all up all together. Yeah? So that function right there is a super easy way of saying, how bad are you at this? And we want to minimize that function. So we use calculus. Let me explain. By the way, this is what it looks like. It's a big W. This is what the H looks like for us, right? We see, I wanted to go back, and this is the big matrix times the X plus the bias minus Y. And the sum is out there, remember, because this produces 9 numbers. We add them up. Right? And so 9 numbers here, right? 9 numbers here. We subtract them, find the length of that vector, and we want it to be 0. Yep. Okay. So we're going to use our trusty calculus. So remember this function right here, x squared. What is the minimum of that function? 0, right? And because this is the x, and we want to find the minimum of this. The minimum of this function is at 0. Where does that function minimum equal 0? Well, at x equals 0. But pretend you're blindfolded and you can't see this, and you're standing in this function somewhere. And you want to know, which way should I go to get to the minimum? If you're standing there, which way do you want to go? You want to go down. So you put your foot back, because in this dimension, you're like flat Stanley, right? There's only 2 ways you can go, left or right. And so if you take a step back, you're like, oh, that's up. If you take a step forward, that's down. That's where you want to go. But how does the little man in the computer know what's down and what's up? Well, if you're here, let's just say if you're here, how do you know that this way's down and this way's up? Well, you've got to find something called the slope, right? Because if the slope is going down, you know which way to go, right? So it turns out that for any function, the slope is this little piece in y and this little piece in x. So dy divided by dx is the slope. And you probably remember taking calculus or hating it, and you had to write down dy divided by dx, right? That turns out to be the derivative or the slope at that point. And so with the derivative of this function, you stand there with your eyes closed and be like, okay, derivative, what's the slope? And now we're going to be a little bit more clever, because we need to tell it mathematically which way to go. So I'll just tell you that the slope of this function at every point is 2x. Okay? So let's just say we're at 3. We're at positive 3. What is the value of the function at positive 3? Well, 3 times 3 is 9. What is the slope at this point? 2 times 3 is 6. So we know the value is 6. And what direction do we want to walk? Positive or negative? We want to go in the negative direction, but the slope is positive. Okay, let's go over to negative 3 here. The value of this function at negative 3 is still 9. What's the value of the slope or the derivative? Minus 6. Well, we want to go positive direction, right? And so it turns out that if you go in the direction of the negative derivative, you are going to go the right way. But here's a scary thing, okay? The slope of at 3, minus 3 is negative 6. So, all right, let's just go positive 6, right? Because we want to go that way. Where do we end up when we go positive 6 over? We end up at 3, right? Because you're at minus 3, and then you're going 3 more. 6. Okay, we're at positive 3. We want to go in the direction of the negative gradient, which happens to be negative 6, right? So where do we end up? And that man in the computer will walk forever and ever and ever, missing the point. Right? So we have to scale the steps we take by some value. And this my friends, is called gradient descent. I've just shown you how to think about the algorithm that optimizes functions, right? You start with the best, you start with a W, you don't care where, right? And you take a step in the negative gradient of the cost function, but we scale it a little bit so that we don't bounce back and forth. Are we okay with this?
Why would you want to analytically come up with a derived?
What's that?
Why would you want to analytically come up with a derived?
Why do you analytically want to come up?
And not just say, okay, we're going to take the normal function and then go up an x, go down a bit.
Because in multiple dimensions, right, this actually turns out to be a vector, right? And so you have to take a step in a really interesting direction because, like, in 3 dimensions, you have a derivative, like, in 3 different ways. And you have to, like, okay, where do I go from there? Right? And so, and it turns out that I don't know how you know which direction you should go in because we never see the function, right? Like, we don't see it. The computer has no idea about the function. All it knows is what the derivative is. And that's all it uses to guide it to the right area. And this learning rate is important, right? Because as you're optimizing your function, if the cost function is going down, all of a sudden goes up and keeps going up, you diverged. Your learning rate needs to go down. If your cost function just gets smaller, but by really tiny amounts, and it's taking forever to get to 0, maybe you should make your learning rate bigger, right? And so now these are actual real machine learning terms that people use, right? There's learning rate and cost function, right? And so this is the actual thing. To find this magic W, you also have to do this with B, right? B1 is defined as B0 minus alpha times the derivative of the beta of the bias. Okay. Are we okay so far? Okay. Because when I did this last time, like the other day, I went way too fast. I feel like some people were like, whoa, there's a lot of math. It is a little mathy, but hopefully you can see like some intuition. If you don't understand it 100%, right now you're still better off than almost all people that pretend they know AI. Okay. So far, we've looked at X, an incoming picture, which is a vector representing an image. We found a Y. We have a Y, which is the right answer. That's also a vector, remember, that represents on or off, depending on the number that you have. Then you have this thing called the model function, right? H of X. We decided we're going to do W transpose X plus B. This is an actual matrix, so that the answer that comes out is one of the 10. It's a vector of length 10, where the highest value will tell you which one it thinks it is once we do the optimization. The loss function is the function that we figured out that we want to minimize. This is called the squared error function. And then the optimization that we're using is gradient descent. Okay, so this is our first machine learning algorithm. Let me show you how you write it in Tensor Flow. Okay, has anyone heard of Tensor Flow before? Okay, you've probably used it. Okay, so Tensor Flow is interesting because the first time you use it, you're like, what is this doing? Because you write all this code that doesn't do anything, and then you write this code that uses the thing that you thought wasn't doing anything to do something. So you have to define a graph. Here, I'll show you a picture. You have to start a session and run. So, like this, nothing's happening here. All you have to define this graph of things, because TensorFlow is just this way of creating like these big structures and then optimizing them. And we're going to create a structure for hours, and you'll see what it means. We have these things called placeholders, which are promises to give TensorFlow some values. We have these things called variables, which TensorFlow can optimize. And then we have these things called constants, which are, well, constants. And then we take these things and we build some graphs, right? For example, W is a variable that we want to optimize, right? And we're going to take W and dot it with X. So now, remember, there's W coming in and X, and then there's this node, W transpose X, right? And then we have this B over here. You see how it's starting to make a tree? So let me show you what that looks like in code. So this is a TensorFlow. Here's my placeholder for X. Notice that it's 784 wide because that's how many pixels we have for the picture. And then the classes we want are between 0 and 9, which is 10. The reason why this is none is because we're saying, I'll tell you when I tell you how many examples we have. Okay. The next thing we want to do is we want to make a predictor, which is a linear model, right? And you're probably wondering, what does this function look like? Well, I'm glad you asked. It looks like this. We have W and B, which are variables. And what we're doing is we're taking, this could have been switched around, but I didn't. This is W transpose times X, adding B. Are you seeing how this is working? It's exactly what we decided we were going to do. Now, accuracy is just a measure of, did it get it right? And accuracy is different than the actual loss function, because accuracy, right, what we're taking is just the maximum one but that it thinks it is, and we're saying, did you get it right or did you not get it right? The cost function is saying we want to reduce the, the squared error of both vectors. So in this case, we're getting an actual answer. Think of it like an absolute value. And in this case, what we're doing is we're trying to find the difference between the right answer vector and the vector that we produce. And we want that to be as small as possible, if not zero. Okay. Oh, by the way, notice that it's the function minus y, right, which is h of x minus y squared. We're summing them up and then dividing by how many there are. So it's pretty similar. It's like 1 over m sum, right? Do you see that? And then this is the hardest part, obviously. The gradient descent optimization is, of course, this. All right? We take this. We say we want the gradient descent optimizer. What is this again? It's the alpha, called the learning rate, which tells it how many steps, like how to scale its steps. And then we want to minimize this cost function, which happens to be this one. That's it. Notice we haven't really done anything yet. We've just defined this graph. Okay. Let me show you what that graph looks like, so that, because I worry that, okay, here's this. Oh, this is Visual Studio, if you haven't seen this before. And then here's my output. We want the logs. So this is something called Tensor Board. You notice that I have this interesting code that says, like, gives it everything names, like the label. Here, let me show you. So it's like here, I give these things names. You can see also up here for everything, I'm giving these things names. When you do that, Tensor Flow is really nice in that it actually gives you, hold on, is it running yet? Sorry, hold on. Oh, it's still thinking about it. So, man, it's not loading up. So when this loads up, it'll actually show you what the graph looks like, right? With W and the B coming in, but for some reason it's not starting right now. Maybe it's because I have, what's that? Okay, let's do that. Let's try one more time. Well, I'll let it think about it, and I'll go on, because I'll show you these graphs of how this stuff runs. Okay. Oh, did it work now? Oh, it did work now. Okay, here we go. Oh, it actually ran twice. Okay, so let's go to the graph here, and let's take a look. There you go. We built this TensorFlow graph, right? You can see it's 784 by 10. The bias is 10. The input is something by 784. And then the model function, we multiply those two together with the dot product. Inputs and then the outputs, right? This output thing is used in the loss function that then is optimized. You see how TensorFlow made this graph for us? It's really nice. Okay, so now we have to actually run it. Once to run the graph, this is what it looks like. It's a little bigger, and you're probably gonna be like, wow, that looks like a lot of stuff, but it's not once we get into it. This is just loading the data up. This is creating a bunch of summaries for me to see what the loss is and what the accuracy is. And then this just initializes the variables to something, right? When I did you can see when I did these things over here, Notice that there is this init function that says just initialize them all to 0. Do you see that there? So that's why I have to call this initialize. And then in order to run a graph, you have to create a Tensor Flow session. And that session, once you start it, you can start doing things. And all I'm doing is I'm just looping over all the data. And right here, I'm running the optimizer. I'm looking at the cost. And then I'm running these merge variables, which are actually writing out like the summary of everything. And the summary, you remember, is the accuracy and the loss. So what do we want to have happen as this thing runs? We want the accuracy to go up, and we want the loss to go down, right? So this is what it looks like when you run it. And I just made a video of it because it's a lot easier to see, but I could run it on my computer and it would look the same, except I changed the text to green. Right? Notice that on my device, it runs really fast because TensorFlow uses the GPU if it sees it. And if you have the right version of TensorFlow installed. Notice that the cost function is indeed going down, but not very fast, right? And it's almost close to 0 anyways, right? And I actually should have sped this up, but I didn't because this is how fast it actually goes. Right? I could have like sped it up, but I'm not a marketing guy. I only thought of that right now. How good is it doing, by the way? I only had this thing run 10 times, by the way. Is it getting smarter? Is it finding a better W at each epoch? It is, but not by very much, right? And then at the end, it'll tell you the accuracy. Was the accuracy okay? 86%. Let me show you the graph of how it did over time. This is the graph. By the way, we want the accuracy to go up, and we want the loss to go down. So there you go. Okay, well, notice that it was like got smart, then got really dumb, and then got smarter. Right? If you see these kinds of things, that's a bad thing, right? You want to always see it go up, and you want the other one to go down. That's how we debug stuff in machine learning, right? We're like, okay, is it getting smarter? But if like you get the opposite on both, you need to stop. Just stop it, and then start over. Okay. Okay. Any questions about TensorFlow? I showed you that graph, but I showed you a better one, which is a more real one. So is this deep learning, what I just showed you? No, it's not. It's just a single, it's called the perceptron algorithm, if you're wondering. And it's just a linear combination of the inputs to produce the right output. Right? Because our data we're assuming is like this, but what if your data is like this? There is no line that will solve that. So you have only two options. You can change the data as it's coming in, or you can change the H function. And you're probably wondering, well, why would you ever change the data? There is an algorithm called support vector machines, which effectively projects your data into a new space, finds a line, and then projects it back. But we're not talking about that one today. The one we're talking about is neural networks or deep learning. And so you've seen this diagram before. Well, why don't we do this? Why don't we do the same thing we did before, which is this thing? Remember, if you forget all this other stuff, this is what we did before, right? But let's just stack them up together, right? And then come up with an output. Is this deep learning? Neural network. Is this neural network? This picture that I showed you, is it neural networks? No, because it turns out that a linear combination of inputs followed by another linear combination of inputs is still just a line. It's just a line. So you have to introduce these things, a little function. So on each one of these inputs, you're going to take all the x's and the b that we had before. We're going to do the dot product thing we did before, and then we're going to run a function over it. That's not linear, and that's called the activation function. Okay? So this is where like like, I feel bad, right? Because I always, like, when I do this talk, I can see, like, you follow me, like, really well. And then all of a sudden it's like, whoa, there's a lot of stuff happening before. A lot of stuff happening. So remember, this is the thing we just invented, which is, if you just look at this one thing right here, that's the dot product that figures out the horizontal or vertical. When we add these other ones, this is the dot product with the matrix that figures out 0 through 9. Now we're just stacking them, but then adding a function every time that we run on each of the nodes. That's it. I don't know. Like, usually in the middle, I put a rectified linear unit activation function and do some kind of softmax at the end. But any differentiable function will work. Well, it will work with the optimization algorithm. It may or may not work with your data. Yeah. So let me show you what this looks like in code, right? You notice that really not much has changed, right? We still have X coming in, Y coming in, and now you see this predictor is a little bit different, right? That's what it looks like. Remember, we had W and B, just like we had before. W is a matrix, B is a vector. We have this layer, right, where we do the actual multiplication, and then we take the activation function. Now, the reason why I'm doing this is because I'm saying, okay, I want 2 hidden layers that have 256 units each. And so our network, well, let me show you what it looks like. Looks like this. Like, it was almost like exactly the same thing we had before, right? Except we have the model loss and the optimizer. But here now we have some more layers. That's it. We're just adding another layer. Because we added another 2 layers in there, and then we do the model function, which is the matrix multiply times the matrix multiply, and then we optimize the loss function. Does that kind of make sense? Let me go back. Here you see that I'm creating an input layer. The last output layer is X. So for the first one, we do X times B plus X times W plus B. And then we loop again with the last output. And then we go again. And then one more time. So we have the input X, 256, 256, the output, which has to equal 10, right? Now, I'm going to give you these slides so you can look at it. And this code is on GitHub, so you can look at it. Okay, but I want you to understand that we started with a simple line. We just added some lines in between, but then we put a function in it. Okay? And then I changed the optimizer, too. The optimizer looks like it's just like the same like before, except it's called Atom Optimizer. And the Atom Optimizer is just gradient descent, but it's smarter about the steps that it takes. Instead of swinging wildly, for example, it measures like the momentum so that it's like, I don't want to go that far over there or that far over there. So it takes like kind of average. And then the other one uses like RMS prop, which like hits the steps a little bit longer into the right direction. And that's what Atom is. Just gradient descent plus some extra flourishes. Okay. All right. So I ran that one. And you can see is that algorithm better than the other one? Well, it got smarter faster. I bet if I ran it more, maybe it would get smarter. But it looks like the actual like accuracy is about kind of the same, and the loss function kind of hovers around. So it's not that good. This is what it looks like, by the way, when it comes in. The input comes in, and then like when you're doing the actual h of x function, the x comes in, you multiply them, you get the product, you add them, you do the ReLU over each one of those items, and you do it again, add features, blah. That's what. So when you're thinking about, well, what is the model? What is machine learning actually saving? It's saving vectors and matrices. That's it. So when you get this model that you package out, you're literally saving 1, 2, 3 matrices, 4, 5, 6, right? Because you need the B vectors and you need the W matrices. So 3 W's and 3 B's, that's what you're saving. That's not very sexy, is it? Like you're thinking it was like, there was like a little brain that you were making. No, you're making matrices, W's, and B's. That's all you're doing. And that's what deep learning is actually saving. And it turns out that if you're doing deep learning is a neural network that's very deep, that has a lot of actually connected, interconnected layers that are very deep. So now the question is, how do you get the derivative of this function? Right? Because that's what we need. With the little man in your computer that's walking around blindfolded, needs to know the derivative. In multiple dimensions, the derivative is called a gradient. I don't know if I told you that, but the gradient gives you a vector of the derivatives in all directions. So here's an interesting property of derivatives. It turns out that the derivative of a contained function is the derivative of the outer function times the derivative of the inner function. Okay? And you may or may not know that, but it's interesting because if you want to find the derivative of this layer, which is what we want, that's the output, we need a derivative of this layer times the derivative of this layer. And if we want this derivative, we need a derivative of this layer times this one. And all the way back. It's like it back propagates. And so whenever we're finding the optimum, we're actually passing the x's forward, optimizing backwards. And that's called the back propagation algorithm, or back prop. You've probably heard it that way. And so the way I think of this thing in my head is like there's this little man walking around trying to find the computer man, trying to find the low points. And the way he does is he goes boom, boom, every time. And this is happening a lot. And there's a lot of matrix multiplications and functions happening, a lot. If you have 1 million examples, it's doing it more than 1 million times. It's like, I wish we had devices that were really good at multiplying matrices. Oh yeah, GPUs, right? Because when you do graphics, all you're doing is multiplying matrices. That's why when you run on a GPU, it's faster, because it's like graphics. But it's actually a little man that's blindfolded walking around trying to figure out where the lowest point is. Okay? Okay, so here are some hints that, because I work for Microsoft, and you're probably wondering, well, he just taught us how to use something from Google. Yeah, because I don't care what you use as long as you use my cloud, right? If you run it on my cloud, it's good for me. Use whatever you want. TensorFlow people use, so I'm going to show it. Okay? So let me show you some cool ways of actually doing that. As you can see over here, there is this really cool thing, and this works on Visual Studio Code too if you're on a Mac. We have these things called AI tools for Visual Studio and Visual Studio Code. So remember how I ran it and it took a long time? If you don't have a GPU and you run it, it's going to take a very long time. So what if you want to do these things, but you don't have like this beefed up machine? That's okay. We have beefed up machines, right? Mine is called Viking because Vikings are beefy. This has 4 GPUs on it. And what I can do is I can right click on this and submit a job directly to my remote machine. And if you're using Visual Studio Code, that's great too. So we don't, like, if you have a Mac, this works too. It doesn't, we don't care. So imagine being able to, like, let me try this, submit the job. Let me try this, submit the job. Let me try this, submit the job. Now you have 4 GPUs like actually doing stuff other than mining Bitcoin. That might actually get you a return, right? So now the question is, well, crap, what if I don't want to stand up a machine? I just want to have stuff come up as I would like. Well, we have these things called, we have this thing called Azure Batch AI. Oh, it's refreshing. Give it a second. I think I only have 1 cluster running. But what this does is if you submit a job to Azure Batch AI, it'll spin up the resources that you want and then spin them down when you're done. It's called HAL. Anyone? HAL? I'm such a nerd. So now, but then there's this other thing. You're like, well, what is that thing in the middle? Well, let's just say you're working in a team of data scientists. Like, the problem I've seen, and I'm guessing that maybe some of you have the problem, is that data scientists, some of them work like by themselves, and they build these models on the data, and they have their own folder structure, and they've tried all these things, but you don't know what they've tried. So when you come in and you're the new guy or the new gal, you're sitting there thinking, I'm going to try this, I'm going to try that, and they've already tried it. So how do you keep track of the runs that you've done, the parameters that you've used, the network topology? Because notice I use only 2 layers. What if you want to use 4 or 5? What if the learning rate is different and it did a lot better? What if you use it? So in Azure ML, we have something called experimentation service, which allows you to keep track of all your runs and how they did. What's the output of machine learning? Well, it's a model, and for us in deep learning, it's just a bunch of matrices and vectors. Where do you put those? Well, it turns out we have something called Azure ML Model Management Service, where you put the models up there and you version them. You give it 3 files. You give it the actual model, which is usually like some zipped up matrix files, usually pickled if you're using Python. Then you have this file that runs it, that loads up the pickle file, takes an input, executes the model, which is a bunch of matrix multiplications, gives the output and spits it out. And then you have this other file that says, what should I expect as input and what should I expect as output? So that you package that up and put it up with a version into our model management service. Where do you run this? Well, we have something called the deployment service, which once you set up an environment, you literally just say, deploy this model to this environment, and then you have a REST service, RESTful API that you call and gets paid back. Now, you're probably thinking, Seth spent a lot of time talking about machine learning, because if I would have started with these services first, this would have been the most unsexy thing you've ever seen, right? But now that you know what it actually means to do AI, specifically machine learning, you know you need to do experiments and need to keep track of runs. You know you need to keep track of models, just like you do any other bit of code that you, not code, but what do they call, artifacts that you put out. There's another artifact, the zipped up bunch of matrices that you learned over a long period of time. And then you need to have a place to actually run them. So with Azure ML, we have all 3. We have experimentation, model management, and deployment. And in the background, when you set this up, we're actually setting up a Kubernetes cluster where we're Dockerizing your actual model with those 3 files that I told you, and it puts up a container that you can just call. Now, if I would have led with that, you would have thought you're not as cool as the other ones that have cool names for computers or things that talk. But we're not an ad company, right? And we're not a store. We actually make things for developers. And this is what you need if you're going to be doing this. Now, if you don't want to build your own models, we have something called cognitive services, which have pre-built models that you can just use. Okay, does that make sense? Yeah. Sure.
If you look like 5 or 10 years from now, to what extent do you think people will be building their own models as compared to using a service like cognitive services?
So the question is, and I want to repeat it for the microphone, the question is, in the next couple of years, are people just going to be consuming models, or are they going to be building their own? Well, I don't know if I told you, but I worked for a component company before I started working for Microsoft. Like, for example, did any of you know how to write a PDF from scratch? No, I don't ever want to learn, right? We just buy something and it does it, right? I imagine a scenario eventually where we have a bunch of models that you train that somehow you submit to a store and that you pay a subscription, because notice that these models will get dumb if you don't keep training them. You give it more data and the W's get better, right? Because your W's, the data might change, so your W's might get out of date. So you have to give it more data. So imagine subscribing now to models that you buy or use or consume. Yeah, absolutely. That's right. And it turns out that if you start hoarding data now, it's actually the data that will make these W's better than anything else. And so I imagine a scenario where niche, like insurance companies start making models that they sell, right? Or the government starts producing data that then people can use to make models, right? But the challenge here is, and this is where we have to be careful, is your computer is dumb. It will make W's based on the data you give it. So if you give it biased data or data that's harmful, it will learn to be biased and harmful. And so now we need to start, that's when you need to start thinking about ethics. Yes? Not very much. I'm almost done. Sorry. I already showed you. Oh, see? Look at that. Awesome. You didn't even have to make it awkward then for everybody. By the way, I actually ran this using something called a convolutional neural network, which is what you should use for MNIST. Look at this. That's the loss function. And that's the accuracy, 98.6. And so just by changing the architecture of that neural network and optimizing it using a smart optimization, I can get 98% accuracy on models that look like this. Because how do we use these models? So this is a WPF app that's using the model that I built called from Tensor Flow called digits.pb, which is just a bunch of weights. And now I can oh, yeah, I confused it. It's pretty good though, right? You're probably wondering what the code looks like. I take the data from the canvas, the ink canvas, and I create this vector that it expects, right? Which is this grayscale 28 by 28 image. And then I import the graph, the TensorFlow output, and then I add the input, which is the input, and I fetch the output, I run it, and then I get the value. And let me show you as the last little bit what that actually looks like. So debug. That's a bad 3, so it might have a hard time. Those are the numbers that it gives you, and you pick the biggest one, which happens to be 3. You see the input is that long vector, it's 784. The output is another vector that's 10, and you just pick the right answer. That's it. Okay, so to finish up, here's some stuff that you can actually go look at and download. Feel free to download if you want to get a hold of me. There's that. Thank you very much. Yes, sir. Any questions? Thank you very much for your time, my friends.